Name. There we go. What? Okay. So. What is that? What? That's what you call Kessler? When I was student teaching, they wanted to call me K-Dog. You can't call me K-Dog. Yeah, 5th grade. All right. Okay. Part of the reason why I love calculus is calculus kind of brings you back in time. Okay. When I say back in time, the idea is that you're sitting there with the ancient mathematicians, and you try and encounter some of these problems. For example, the question of the day is, what is that? Do you guys know what that looks like? Yeah, it's a woo. Very good. That's what that, you know what that looks like. You got a general idea, but that's because you've graphed it enough, okay? So here's just an idea, though, okay? Larry's going to say that this shape looks something to the nature of that. You guys would agree, right? And what we could do is we could generate many points on our, using a table like X, Y values, and we could come up with a lot of dots that would fit that, right? For example, you could, plug in a bunch of points. You could have a point plotted here, there. But my question is, unless you plot every single point, can you be sure that the graph doesn't do something like... Because you know it's 3rd degree. Okay. But, you know it's 3rd degree. Very good. But, what you know about third degree equations and their behavior, that is something that you end up verifying through calculus. So the reason why you know it does that has to... You know that a 3rd degree equation has at most how many maxes and mins? 2. And a 3rd degree equation has how many points of inflection? 1. But you verify that through calculus, right? That's why we know that behavior. Now, you've been told for the past 2, 3, 4 years that, they look the way that we first drew it. But it's verified in calculus. If you were to draw this has 1, 2, 3 different inflection points. So this would be a 5th degree polynomial. But so think about the people back in, 500 years ago, before that graphing calculators and stuff, they were to verify it. That was part of the use of calculus. So again, we want to come up with really good ideas for what these look like, and we're going to, do you know what that looks like? Yeah. Yes, really good questions, Emma. Why would they have to graph something like this? Okay. So, okay. Can I give here's the answer to Emma's question, okay? This is awesome. All right. No. Part of it, we often ask, why are we learning this if we don't really know any use for it? And again, I'll go back to what I said last year. Remember about imaginary numbers? They said we now know that they're there, but what good will ever come of them? Well, 200 years later, Leonard Euler came along, and he discovered alternating current for electricity based off the theory of imaginary numbers. And because of that, we now have, one power station for, the city, whereas if you had direct current for electricity, you'd have a power station every block. So thank goodness we have alternating electricity. That is only possible through imaginary numbers. So sometimes studying mathematics, history shows that studying mathematics, not for the sake of having a means to an end, but for just the purity of math, generally results in great things. But so I asked that same question, Emma. Back when I was about your age. I was a freshman in a college. Okay, I just spit on you. Yeah. So I'll back up. All right. Let me give you a new sheet if you want. So, and I probably told you this before, but I said Dr. Khan. Okay, that was his name. He worked at the Mayo Clinic, and he had come to teach us mathematics at the College of St. Olaf. And we said, tell us about the wonderful things of the world that really matter. You know, and we were people who loved mathematics, but we're like, you know, we know that most things we do in math never really result in anything. He looked at us, he was like, are you nuts? He said, well, come on, you know, when we ever like graph a polynomial, you know? It's like, well, let me tell you. And he told us about how he was, you know, working in the hospital. And here was his job at the hospital. How cool would this job be? He was a problem solver. That was it. Doctors would come to him, and they'd say, we have a problem. Can you help us figure it out? There's probably something mathematical to it. We don't really know, but we'll just explain it to you. And you go to your little workshop for a while and come back and see what you can give to us. And so he did. And so here's the deal. Doctor came to him. I know I've told you part of this story before, but this is how it relates. So, it's an artery. Okay, what happens to arteries sometimes? Yeah, you get all this buildup, right? So that hardly anything could get through there. You got just like a little bit. What do you have to have when you got a lot of buildup in an artery? Okay, so sometimes you have a stent, which actually like opens it up. The other thing you can have is a bypass. And what a bypass is it's literally, you cut the artery in two places. And what you do is you put another piece of artery in there so that it can go around. It can bypass the blockage. Okay? So that's what they do. And here's what the doctor said. He said, Mike, I'm doing this operation. He says, here's what I want to know. He said, when I put this artery, or when I put this branch on here, he says, I know that it forms an angle. Okay? And I know that the blood is flowing this way, okay? It's going to, get there. It's going to end up going back over here. He says, I fear that there's a lot of pressure right on this spot, okay? That's a very critical spot. He said, what should theta be in order to minimize the viscosity of the blood flow, or the friction of the blood flow? He's like, I don't want a lot of friction in the blood flow right here because I'm afraid that it could damage, the connection that we have. So what angle do I create it to minimize? Well, when you think of minimize, what do you think? You think of a function, and you think of which spot of that function? The minimum, right here. And when you think of the minimum of a graph, you think where the starts with a D. Derivative is equal to 0. Oh, back then? Oh. No. Now, remember what was one of the primary reasons why calculus developed at the time that it did? What were they trying to prove? That the Earth was not the center of our solar system, but rather the sun. I mean, there was many years where everybody said the Earth was the center. We would have to take a lot of astronomy classes to be able to do the work that they did. But that is one of the founding principles why. Okay, so all your statistics stuff. Okay, whenever you take a stats class and you wonder where all that stuff started, okay, Pascal and Bernoulli, these guys back in the Renaissance era, they decided to head off, to basically go gamble, and the whole study of statistics and probability really resulted from they wanted to be really good gamblers and try to beat the house. That's what they wanted to do. They were really good, yeah. I mean, they made a lot of money. But they also did there's a problem that resulted from the study called the Gambler's Ruin that shows. So, okay, I promise to go on after this. If you got, Larissa, how much money you want to go to the casino with? Okay. All right, great. You want to go? Okay. No. You're gonna walk into a casino and you're gonna say, "I'm gonna bring some money with me." What are you gonna? How much are you gonna bring? Are you 18, by the way? Okay, she's 18. Totally legal. All right. Just pick a number. It doesn't matter. $100. Larissa walks in with $100, and she's going to play. She's not going to play blackjack. That doesn't really count because there's a different method at. But she's going to play a game that involves complete chance. She's going to play the roulette wheel. Now the roulette wheel is the #1 way that you can win because the roulette wheel has it has 2 colors, right? Red and black. And are there an even number of the red and black? No, it's pretty close. There's like, say 23 of the red, and there's like 25 of the black. And if you get red, you win. And you also get to pick a number along with it, right? So you get a pretty good chance, like 23 out of 48 or something like that. It's like a 45% chance of winning is what it amounts to. Really good chance of winning. Let's say that she's going to play the best game, okay, for her chances, and she's going to play this way. She's either going to take that $100 and she's going to play until she doubles her money, or she'll play until she has none left. Anybody want to guess, even playing roulette wheel, what percentage of the time your game ends with no money as opposed to $200? What percentage of the time? 97% of the time. We got to learn more math in order to see it, but you can see we can look up the Gambler's Ruin problem right here in my probability theory book, and you'll see exactly how it works out. You might not understand all of it, but it does in fact work out that way, that you'll lose 97% of the time before doubling your money. So that's what Sawyer is. You lose. So a lot of mathematics resulted from interesting stuff, and let's get to it. Here we go. You want to learn about what? Gambling. Yeah. Okay, there's your 2 cents for the day. Okay, so guidelines for curve sketching. Okay, things we should consider. Domain. How would you describe domain to somebody? Yep, your x values are your inputs. So we need to consider the inputs we can have. How about range? Outputs. Hey, this is back from last year, college algebra. Intercepts. How do you find the x-intercepts? Find the x-intercepts, you set y equal to 0 and you solve for x. How do you find the y-intercept? Set x equals 0. Symmetry. Do you remember all your symmetry tests from last year? So we'll just forget about it. Okay. But there are certain graphs that are symmetrical. For example, are parabolas symmetrical? Yes. And so you should think about that as you're, generating graphs. Yeah, in that situation, but we actually had tests to see if something's symmetrical about the x-axis, the y-axis, the line y equals x, the origin, all that stuff. Now here's something really important. So this is the new part. Asymptotes. Where do you end up with an asymptote? You might get an undefined value for the normal domain. So let's say your domain is negative infinity to infinity, but when you look at the function, you then find that there's a domain restriction where you can't have x equal to, say, 2. A lot of times you're going to have a vertical asymptote there. Now, if that discontinuity is removable, though, you just end up with a little dot. Remember that when we graphed that in class? You just had a little dot? So there are situations where you don't necessarily end up with an asymptote. But here's the other part, okay? Are those vertical asymptotes or horizontal asymptotes? Vertical. But you can have horizontal asymptotes, and that comes from what we just said. Okay? These are vertical. The horizontal ones, the way that we define the horizontal asymptotes is we let x go to infinity. And we let x go to negative infinity as well. And that tells us really not necessarily just the asymptotes, but the end behavior. So sometimes we'll come out with an actual asymptote. Sometimes we'll come out with it just goes off to infinity. Depends on the type of function. Intervals of increasing and decreasing. Increasing happens where what? F prime of x, very good, is greater than 0. And decreasing is where f prime of x is less than 0. Local max, local mins. The first derivative is equal to 0. If you're a max, are you concave up or concave down? Yeah, if you're a max, you're concave down. So f double prime of x, whoop, not triple prime. F double prime of x would happen to be less than 0 for a max. And for a min, f double prime of x to be greater than 0. So concavity, we kind of already said it. It's concave up if f double prime of x is greater than 0. And it's concave down if f double prime of x is less than 0. And what happens if f double prime of x is equal to 0? Very good. We have inflection. So this is a nice list, and so when the development of calculus happened, this is one of the nice things is that you could really get a good graph. And our next section is actually on optimization. So the story I just told you guys about the artery, we're not going to do that problem. If you'd like to, we could spend 15 minutes one day. We could show you that problem actually works out. But we're going to do problems like this where you apply the study to the real world so you can see the purpose of it. So let's do a problem that you're very familiar with. Let's do number 1. Use the following guidelines to sketch the following curve. X to the third minus 2x squared minus 3x. I'm not going to do the derivative yet because the first thing I'm actually going to do is we're going to add some pieces to this. We're going to start out by looking for x and y intercepts. Let's identify the y-intercept right away. If you plug in 0 for x, what do you end up with for y? So the y-intercept is 0, so it crosses at 0. Let's find the x-intercepts. And if you can't find the x-intercepts, don't worry about it. But this one is actually pretty easy. 0 equals x to the third minus 3x squared minus x. What do you do first? Oh, minus 2x, excuse me. What do you do first? Oh. So very good, we take out an x, we get x squared minus 2x minus 3, and then so what are the x-intercepts? Yep, -1, 0, and 3. Well, that's some helpful information to be able to understand how to graph it. Something else we need to do. Anytime you see this, if I list asymptotes, you should also write EB for end behavior, okay? That means what does it do as x goes towards infinity or as x goes towards negative infinity? And so we want to verify this as well. So each problem does take quite some time, but we can handle it. Let's take the limit as x goes to positive infinity of x to the third minus 2x squared minus 3x. How did you evaluate that limit? What did you do? Take out an x cubed. So you have the limit as x goes to infinity of x cubed times 1 minus 2 over x minus 3 over x squared. What's going to happen? Yeah, this inside here, it will be 1 minus 0 minus 0, which is just 1. So if you're headed towards positive infinity, you'll have a large number to the third power, which will be infinity. And then, as x goes towards negative infinity, you would have a very large negative number to the third power, which would result in negative infinity. So, we don't have any vertical asymptotes, and we don't have any horizontal asymptotes, but we do have end behavior that we could talk about. And here's how we write it, okay? As x goes to infinity, y goes to infinity. And as x goes to negative infinity, y goes to negative infinity. That's the end behavior that we know of this function. So that kind of ties off pieces that are a little bit new to us. That's the purpose why we looked at limits headed to infinity the past few days. Now we want to get to the other pieces that describe this function, which are intervals of increasing, decreasing, concavity, max, mins, and inflections. What do I have to do for those? Find the derivative. So let's take the first derivative. F prime of x is equal to what? 3x squared minus 4x minus 3. Set it equal to 0. Does this factor? No. That's a quick way to check is do the AC method exactly like Larry did. If you move this 3, or if you multiply the last one by 3, you get x squared minus 4x minus 9. You know x squared minus 4x minus 9 does not factor, right? So therefore, this will not factor. So what would you do in this situation? Quadratic formula. Can somebody quick plug in quadratic formula? We won't, just give me the decimals that we get. .87 and negative 0.54. Okay, so those are our first derivative points. They are going to come in handy here in a second. Let's do the second derivative as well. F double prime of x equals, what is the second derivative? 6x minus 4. So that equals 0. 4 is equal to 6x, so x is equal to 2/3, or 0.67. We okay with that? We're now done with the algebra. Now we just need to kind of sort it out, plot our points. Okay. I'm going to put my first derivative on top. And my second derivative on bottom. I'm going to give myself a little bit of room here so you guys can see it. I'll keep the values there. Okay. Looks like all of our values are between 0, 1, 2, and 3, right? Or negative 3 and positive 3. I mean, if I made my scale to be that, I'd be just fine. Looks like my interesting point for the second derivative is going to be at 0.67, or 2/3. And it looks like my interesting points for the first derivative are 1.87 and negative 0.54. Let's do some interval testing here. What number less than negative 0.54 would you like to plug in? Negative 1. Negative 1 squared is 1 times 3 is 3. Plus 4 is 7 minus 3. So will that be positive or negative? Positive. What number between negative 0.50 and I get a negative? If we plug in 2, we get 4. 12 minus 8 is 4 minus 3 is 1. So that's positive as well. Second derivative, what number would you like to plug in? 0, you get a negative. And if you plug in 1, oh yes. I was plugging it into here. I'm like, it's definitely negative. I was plugging 1 into here. I was like, what's going on? Okay, yes, you plug in second derivative. Very good. Okay. Okay. All right, so it's time to list our intervals. Intervals of increasing. So let me say the first one. And 1 point. Very good. See, all my work is nicely organized right up there. So again, picture, this is what people were doing, 400 years ago. And then we'll do the same thing and we'll be able to verify it graphically. Decreasing. Concave up. This last part is always my least favorite. Do you know why? Because you got to plug them back in. You always get nasty decimals. Just think of what they used to have to do. I mean, we plug in our calculator. That would have been more difficult. So let's just lay this out first. We're going to be able to figure out the first parts. Obviously, the inflection point happens at what? 0.67. And then the local min, is the min going to happen at negative 0.54 or 1.87? Why? Very good. It's concave up, and it goes from decreasing to increasing. Very good. So there's two ways you can look at it. If you're going decreasing to increasing, that's one way you can recognize it. The other way is if you're concave up, it's going to be a minimum. So our minimum is at 1.87. And our max is at negative 0.54. Very good. So now what I need to do is I need to generate y values for those points. And I'll just use my table, x to the third minus 2x squared minus 3x second table, and we plug in negative 0.54, 0.67, and 1.87. 0.88, negative 2.6, and negative 6.1. Now it's time to put the points down. My y-axis. What would you like to make? What would you like the min and max be on your y-axis to make this graph? Yeah, what's going on? Oh, I'm sorry. What the inflection? Yeah, I typed it in the incorrect order. I thought there was something different. So the local min was what? Negative 2. Negative 6.1, the inflection was 2.6. Okay. All right, so it looks like we got to go all the way down to negative 6, don't we? So I'm going to make my tick marks to be, I'm going to choose to go up and down to up 8 and down to negative 8. So I'm going to go 2, 4, 6, 8. And you can choose whatever you want. This is just what I'm choosing. And now that we have that, I can now plot all my points I have. And notice I have the x-intercepts, right? We already said that was -1, 0, and 3. And the y-intercept was 0. So I can plot all those. -1, 0, 3. We have a max at right there. And about there's my min, my inflection. Right about there. And because we know the max and the min and we know the inflection points, we know that there's not any crazy behavior. So they could mathematically, they could go to another mathematician and say, we've used calculus to verify that we know that this is a smooth curve. We know that it, in fact, doesn't have any crazy behavior, that these are the most important points of the graph. And we know that it heads towards positive infinity and negative infinity because we did find the limits. And so now you can do your most excellent job of drawing a great curve. And comes to my favorite part where I then go into my y equals. I have my curve. I go to my window. I make it look exactly like what I have. I'm actually going to go from -3 to +4, so then I can see it off to the distance there. And looks like my y value. Oh, tick marks every one there. Y's go from -8 to +8. And my scale looks like it's every 2. Whoop, that'll be bad. Delete button. And now, you won't get to use your you can't use the graphic portion of your calculator on the next test. That is exact. I mean, that's as exact as we. I mean, is that not a nice replica? I mean, you would be very satisfied with that, not having a graphic calculator. And what we want to do is we don't just want to graph these. Look at the next ones, people. Tomorrow we're going to look at 3x over x plus 2. And then we're also going to look at 2x squared over x squared minus 1. And we're going to look at x minus sine of 2x. So we're going to see because what does it, do you have any idea what that looks like? You have no idea, and yet we're going to come up with an excellent, excellent sketch. I'm just going to give you a couple problems that involve this curve sketching that aren't rational functions I'd like you to work on. Again, you have Monday off, which is nice. I know you're continuing to study for finals, so I'm not going to give you 5 or 6 of these problems, but please be ready to work next week. We are at a very good spot, you guys. We're already at section 4 or 5, ready to head into 4 or 7 next week at the beginning of the semester. So we're at a good pace. We're not too far from chapter 5. And that's where we add up an infinite number of rectangles. So that's where it really gets cool. So we'll give you an assignment. Okay, Elizabeth and Haley and Jesse and Tyler, we hope you guys are doing well. Here's your assignment. Have at it.